and good afternoon. So today we continue on the system sizing of standalone photovoltaic system. So we continue with step number 5, which is determine the PV array size. So before this, we learn how to design the battery, the size of the battery, and the configuration of the battery. So now we proceed to the PV array. So the size of PV depends on the type of charge controller used in the system. So we have two types of charge controller, which is standard type. Standard type also called PWM charge controller. PWM stand for pulse width modulation. And another type is MPPT type. So this solar charge controller, the function is to regulate the energy flowing from the PV array and transfer it directly to the battery as a DC coupled system. So the purpose of this charge controller or solar regulator is to prevent the battery from the overcharging. It also senses that the battery actually fully charged, or you want to stop the charging process or decrease the current flowing to the battery. Okay. That is the function of the charge controller. So this standard type or PWM controller is not very efficient actually and lack ability to optimize an entire array based on the differences between panels, for example. So however, this standard type or PWM controller is adequate for the country that had almost constant or steady solar irradiance, for example, in the tropical countries such as Malaysia. And also this standard type or PWM controller is suitable for the system with the limited budget. Okay, what about MPPT type? So this one commonly used, which is MPPT stand for maximum power point tracking or maximum power point tracker controller. So this controller usually used in a larger system, or we want to make it the system with the higher performance, so we choose MPPT type. So this MPPT type usually increase the solar array effectiveness about almost 30% compared to the standard types. So to increase the voltage and keeping the current low and the small size of the wire, especially for the long wire, so the most suitable is the MPPT controller. So this MPPT charge controller should be connected to the panel, which is to increase the voltage, we need to connect the panel in series connection. Okay, let's continue with the MPPT standard type of charge controller. So the number of parallel PV string is determined using, so NPP represent as a parallel, this PV represent as the PV array. So you need to round up. Energy required, this is what you calculate in step number 2. Step number 2. Step number 2, energy required by the load. Multiply with K1. K1 is the oversize factor. Typically, we use 1.2. So this oversize factor because we need to consider losses due to temperature, dirt, and mismatch. So you divide with, this is system voltage. that you choose is step number 3, multiply with IMP out. IMP out is the output current from the PV module. You need to calculate your IMP out. So we will go through this equation after this. Multiply with peak sun hour. This is peak sun hour daily. Multiply with Coulombic efficiency of the battery. So usually all of this, the Coulombic efficiency you can get from the you can calculate, or you can get from the datasheet of the battery. So this IMP out, so the output current from the PV module can be estimated using IMP out equals to IMP STC multiply with mismatch factor of the current. So this one represent current. And the temperature factor of the current. Sometimes they put K or S the same thing. KMM current. K temp. This is F temp or K temp. Temperature factor for the current IMP. And the K dirt. Okay. So K dirt usually we represent as a 3% losses, which is 0.97. Okay, let's say for example, the battery that you use in the system is the lithium ion battery. So the Coulombic efficiency of the lithium ion usually exceed 99%. Okay, you can put 0.99, 99%. However, this is only possible when the charge at a moderate current and a cool temperature. Okay. So if the battery is the lead acid, the Coulombic efficiency of the battery for lead acid is 90%, but at the slow charge rate, it probably reduced to 70%. However, this Coulombic efficiency is varies, depends on the charge rate, the temperature, and the age of the battery. So when you calculate your NPP, then you calculate your MPPV. First, you need to calculate IMP out, and then you can find the NPPV. So this is NP out here, the NP to find the NPPV. Okay, after that you need to calculate the current rating of the charge controller. So it's determined by I rating equals to ISC STC. This is the short circuit current at standard test condition. This you can get from the datasheet of the PV module. Multiply with number of parallel string of your PV modules. So this one you can you already calculate in here. Okay, NPPV multiply with 1.25. So this is the current rating of the charge controller. And also you need to calculate the voltage rating of the charge controller, which is depends on the system voltage that you choose before this. So whether it's a 12 volt or 24 volt or 48 volt or 96 volt. Okay. So V rating of the charge controller is equals to V system. Okay. So let's open one example of the datasheet of the charge controller. Okay, example here, this is a charge controller, Tycoon, power system solar controller. So this controller is a PWM type or standard type, same thing. So they have 3 stage. So usually 3 stage is bulk, absorption, and float. Or sometimes they call main, boost, or float. Another example, how many stage? This one also 3 stage, which is bulk, absorption, and float. Okay, let's see this one. This one MPPT. How many stage? Oh, not this one. For MPPT, let's see English, page 13. 13. Okay, this one is MPPT charge controller. It has 4 stage, but the 4 stage is for the flooded battery. This is flooded lead acid. So they have main, boost, equalization, and float. And for the seal battery, which is AGM and GEL, a 3 stage, which is main, boost, and float. Same thing. Bar, exhaustion, and float. So let's see the current rating or the rated current, which is 20 ampere. So from this value, you already calculate in the notes. So make sure the current rating should be greater than what you calculate here. Okay, let's say when you calculate this one, you get 18 ampere. So for the charge controller, this is 20 ampere. So this is suitable for you, 20 ampere, greater than 18 ampere. And also rated voltage, for example, is 12 volt. So this one is the current voltage rating, so it's suitable for the system. So this charge controller can be used for both because it's auto detect, which is you can use whether for 12 volt or 24 volt. This is also same thing, can be used for 12 volt or 24 volt. This is also PWM or a standard type charge controller, but the battery voltage range, which is between 10 to 35 volt. So the current rating, so this is a load current rating, which is 50 amp or 30 ampere. Okay, so if 24 volt is 30 ampere, if 12 volt 15 ampere. Okay, so this is the condition of the environmental. Another example of the PWM or standard type charge controller. This is another electric C12 PWM charge controller. So this one rated PV current. This is from the PV module. The current is 12 ampere at 12 volt only. So the maximum DC load is 12 ampere with auto reset. So maximum PV open circuit area voltage 95 volt. So you need to match the PV module with the charge controller. So regulation method, we have only three stages, which is bulk, absorption, and float. Okay, this is for the PWM or standard type charge controller. So the number of PV module in series per string and SPV, this is the system voltage. So the system voltage should be similar to the voltage rating of the charge controller. So we have seen before this 12 volt or 24 volt. For example, divide with VPV standard voltage. So you need to match with the standard voltage from the PV module. So it is very important to note that the standard voltage level of a PV module, VPV standard voltage, can be recognized from its VMP STC, voltage at maximum power at STC, voltage level as shown in table below. So you need to check in your datasheet of your PV modules. So a relationship between VMP-STC and the standard voltage of a PV module. Okay, because we have a very wide range of the VMP-STC. So to match with the charge controller, so we have the standard voltage level. So let's say when you check the PV datasheet, the VMP-STC approximately 70 volts. So you choose the standard voltage 12 volt. Okay, so if the VMP-STC of the PV module is 34 volts, so you choose the standard voltage 24 volt. Okay, so for example here, let's take an example. Yingli Panda. So this Yingli Panda, the voltage at maximum power, let's say this model. So Yingli Panda YL YL 280. So this is PMAC 280C30B. So the voltage at maximum power is 31.1. So approximately 34 volt. So you choose standard voltage 24 volt. Another one is from BP Solar. Is it BP? BP Solar. So for this one, VMP STC is 17.5 volt. So you choose 12 volt, which is approximately to 17 volt. So from this value, you can get the value for the NSPV. So you substitute here. So you get number of PV module in series per string, NSPV. So the final PV array configuration is NPPV. P represent as a parallel string. So number of parallel string of the PV module by NSPV as represent as series number of PV module in series per string. Okay. So let's say if you get the information of PV array configuration 2 by 5, you already know 2 represent number of parallel string. By 5, 5 represent number of PV module in series per string. So total number of PV module 2 by 5 is 10 PV modules. Okay, then one for standard type. Okay, charge controller. So you already know the PV module, PV array configuration for the standard type charge controller. Let's say you want to use the MPPT type of charge controller. You must start with the calculation of the power. Okay, because usually MPPT type they rate or they give a rating of the charge controller in watt, based on the power rating. So it is common for MPPT type charge controller manufacturers specify their product based on power rating. So P array STC, so energy required, you multiply with K1. Again, we need this oversize factor 1.2 because we already consider the losses due to temperature, dirt and mismatch. Okay, that's why you multiply with 1.2 to eliminate all of this, all of these losses. So energy required, you calculate. So from the load name, watt hour, this is PSH, peak sun hour, daily in unit hours, and the Coulombic efficiency of the battery. So now from this equation, you know the power from the PV array. So the power rating of the charge controller, to determine the power rating, you multiply the P array STC with 0.9. So your P nominal should be greater than 0.9 multiplied with P array STC. Okay. This is also as a safety factor 0.9. So this P nominal, so commonly MPPT type charge controller manufacturers specify their product based on the power rating. For the chosen type of MPPT charge controller, we need to check how many modules that it could support. We use this as array because it can be a combination of PV module in series and parallel. So let's see one example of the MPPT type charge controller. Okay, this is example POCOS. POCOS CISN MPPT 85. So they have 4-stage charging. If you use flooded acid battery, or 3-stage charging for the sealed battery. Acid battery also lead acid battery, yes, SLA. Also automatic recognition, which is 12 volt or 24 volt. This is a manual, use a manual for the MPPT type. So this one can type protection can be outdoor, IP68, dimming function. So the efficiency up to 98% with the MPPT technology. So the ambient temperature, the DOD, discharge protection. So this is all the indicator. Where's the technical? Okay. So this is the technical data. So system voltage can be 12 volt or 24 volt. So this is the maximum charge current, 50 ampere, maximum load current also 15 ampere. So this is the P rating, okay, power rating. So maximum PV input power is 250 watt at 12 volt, or if the system is 24 volt, it can go to 500 watt. So this power rating you can calculate, okay, from the 0.9 multiply with P array STC. Let's say you get example here. Let's say you get 200 watt. So the P nominal is 250 watt. So it's suitable to be used in your system because it should be greater than 0.9 multiplied with P array STC. So usually the maximum input voltage be in max or the MPPT type of charge controller is given and usually much higher than the system voltage. Of course, because okay, this is the V in max from the PV module, not from the battery. So that one you can check here. This one. So maximum PV voltage is 85 volt, which is much higher than the system voltage, which is 12 volt or 24 volt. So this is the minimum operating voltage, 9 volt, and also minimum PV voltage, which is 70 volt or 34 volt. Declare here also the maximum battery voltage is 50 volt. So thus the maximum number of PV module in series is determined using, so in the datasheet given is 85 volt. Okay, so you round down, okay, because this is NS max, the maximum number of PV module in series per string. This is already max, you cannot round up because it will become bigger than maximum. You need to round down. V in max multiply with K1. K1 is the safety factor. Typically for Malaysia climates we use 0.95. Okay, this is because it depends on the temperature. Okay, we use 0.95 because when the temperature is low, of course the voltage will increase. That's why we put 0.95 as the safety factor, which is 5%. Divide with VOC max, okay, open circuit voltage at maximum. So VOC max, you calculate VOC STC multiply with temperature factor for VOC. Okay, why we use this TM minimum? This is temperature of the PV module minimum, because when the temperature low, of course the voltage will be very high. Okay, remember back the graph that you already learned in chapter 3. When the temperature low, the voltage is high. That's why this is TM minimum. Okay, minus this is TSTC. So since the nominal power P nominal or P rated by the charge controller is known, then the parallel string of PV module can be determined. So in the datasheet example here, is for 12 volt is 250 watt, which is the maximum PV input power. So 250 watt you need to divide with NS maximum PV that you already calculate here, okay, from the V in max of your charge controller. Multiply VP and PSTC of the PV module. This is from the datasheet of the PV module. Multiply with 0.90 safety factor. So we also need to check the current if available, rating of the charge controller. The following condition also need to be satisfied. Other than power rating, we need to check the current rating. So ISC STC multiply with number of parallel string, because when we parallel the PV module, of course the current will increase. Multiply with 1.25. So let's check the current rating for this MPPT type charge controller. So this is the maximum charge current. 50 ampere. Okay. So this is the voltage. So maximum load current and maximum PV input power is 15 ampere. Same thing. So the current rating is 15 ampere. So that 50 ampere is at temperature 60 degree Celsius and can only have full current on either panel or load, not simultaneously. So, and you get the power rating and current rating and find the suitable charge controller. As for checking purposes, the actual PV array configuration is used NPPV by an SPV such that total energy generated by PV array shall be greater than the energy required by the load. Okay. So to check, okay, you need to check when you choose number of parallel string and number of PV module in series per string. Okay, from all this equation, you need to multiply with PMPSTC of the PV module. This is you get from the datasheet of PV module. Multiply with peak sun hour for that location daily should be greater than energy required by the load. So you need to check, it should be greater than energy required, okay, for the good design. So make sure when you choose NPPV, it should be less than NP max PV. Okay, when you calculate, okay, NP max PV, and to check this NSPV should be less than NS max PV that you calculate before. So it should be greater than energy required from the load. So we already finished step number 5 to determine the PV array. Now we proceed to the determine the size of the inverter. So in cases where AC load are required, so you need the inverter, okay, to convert DC to AC. So the inverter should comply with three conditions. Condition number 1, so able to handle continuous load power. Okay. P continuous load. Continuous load power is defined as total connected load more than 30 minutes. So P continuous inverter should be greater than P continuous load more than 30 minutes. Okay, the inverter can handle all the power that produced from the all connected load more than 30 minutes. Condition number 2 should fulfill all. Condition number 2, able to handle surge current, especially with the presence of inductive load. So the P10 inverter should be greater than P surge load. So the power of the inverter, which is 10 minutes, in 10 minutes, this power for 10 minutes, the connection of the load, 10 minutes, should be greater than P surge of the load. Okay, present by inductive load. Inductive load usually come from the motor. Condition 3, able to handle maximum power demand. Maximum power demand is defined as total connected load which is not more than 30 minutes. Okay, so this one 10 minutes, this one 30 minutes. Okay, so this maximum power demand. Okay, so the inverter can handle the P surge load not more than 30 minutes. Other than that, the inverter also should be able to generate required waveform. Example, modified sine wave or pure sine wave. Okay, for the good one, for the good inverter, it can provide the pure sine wave and generate required frequency. So for Malaysia is 50 Hz and turn off when voltage drop below low voltage disconnect. So this is what we call anti-islanding. Should have this anti-islanding. So it will disconnect when the voltage is low and consume very low power during standby mode. Okay, this is self-consumption. So very low power during standby mode. So for surge factor, as a guideline, how to know the surge factor. Let's say the load is induction motor, so you can assume surge factor between 5 to 7. If it's a capacitor type, so surge factor is between 4 to 6. Okay, that one is sizing of the determine the size of inverter. So another one is step number 7 is sizing balance of system component. So this balance of system component include all the structure, the cables, the inverter, except PV modules. So sizing of other balance of system components, example here DC cable. Cable size shall be determined with regard to maximum current capacity and maximum voltage drop. The larger cable size obtained from this criteria shall be applied. So the current carrying capacity CCC for string cables. This is for string, okay, string of the PV module. Okay, when you put a PV module, the connection is series. Okay, you need a string cable which is greater than 2 times of ISC STC, short circuit current of the PV module. Okay, when you connect all the series cable into the parallel connection, so you need a array cable. So the CCC of the array cable should be greater than 1.3 multiply with ISC STC multiply with number of parallel string of the PV module. So NP, PV. Okay, the one for string and array cable, current carrying capacity. Another one is the voltage rating for DC cable. So based on Malaysian standard 1837, the installation of grid connected photovoltaic system, MS 1837. So the cable rating, the voltage rating of the cable should be greater than 1.2 of VOC array STC. So this voltage come from number of PV module that you connected in series. So you need a VOC STC for the PV module that you already connected in series. So when you connect in series, the voltage will sum up. So V cable rating is the rating cable, the voltage rating of the cable. VOC array STC is an array open circuit voltage at STC. So the manufacturer of cable has specified the current carrying capacity and the maximum voltage of their cable. Follow their guideline at all times. Okay, to avoid any losses and also to avoid any injured. Okay, for a safety precaution. So this is the size of the cable. A area. A minimum DC cable. So A is the size or cross-sectional area of the cable in millimeter square. Square millimeter. Equals to 2 times LDC cable. L is the longest root length of the DC cable in meter. So this is length. Why we multiply with 2? Because we have cables from the positive terminal and then go back to the negative terminal. So we have two roots. Positive terminal to negative terminal. So that's why you multiply with 2. And then multiply with IDC. IDC is the DC current. Okay. DC current from the PV module multiply with rho. Rho is the resistivity of the wire. If the wire you use copper, so the resistivity is 1 over 56 or 0.017857. If the cable is aluminium type, so your resistivity is 1 over 34 or 0.029412. Okay, so this one you can calculate. So IDC you can calculate whether for array or for string cable. So loss is a maximum voltage loss in the conductor, usually 3%. So loss will be the voltage drop. So the voltage drop will be for 3% losses, so it becomes 0.97. So V min MP is a minimum minimum MPP voltage, maximum power point voltage. In Malaysia, climate at 1000 watt per square meter solar irradiance, the current IDC is very close to IMP-STC, and the effective cell temperature can reach up to 75 degrees Celsius. Okay. So this is Vmin, minimum voltage at maximum power point. So NS is the number of PV module in series per string. So notes, if you multiply NS, number of PV module in series per string will be min MP, so you get the voltage in one string. So this is V min MP for one module. If you connect in series, of course you need to multiply with number of PV module in series to get the V min MP of the string. Okay, other than size of the cable, you need to calculate the blocking diode. So this is a blocking diode that you install usually for each string. This blocking diode different with the bypass diode. Bypass diode you install, it's actually come with the PV module at junction board, but this is different thing. This is blocking diode, which is you install for each string. Okay? But sometimes blocking diode are installed to protect reverse current flow from battery to the module during night time or during low solar irradiance. However, most modern charge controllers have capability to block any reverse current flow from battery to the PV module. So to calculate this size of blocking diode, V diode bypass greater than 2 times of VOC module STC. Okay, the last one is if the system is a hybrid system, so we need a genset, diesel engine generator set. So diesel engine generator DEG is commonly used in PV hybrid system. The application of DEG in SAPV hybrid system can be many ways. For example, to provide continuous base load, to supply peak power demand, or to work parallel with the PV system, or to work as a backup power generator. In example, supply power when power from PV system is not enough. So to design the size of the DEG will be different in each case. So the connection of DEG in a SAPV can be in 3 modes. Let's say series mode. Series modes mean DEG is used to charge the battery and also to provide power to DC loads. Parallel mode, which is DEG, is designed to work parallel with the PV system that provide power to charge the battery and also at the same time supply AC power directly to AC load. Next one is switch mode, which is DEG is used to charge the battery and also provide power to AC load through changeover switch. So it is uneconomical to operate DEG with low load. So in practice, it is recommended to operate DEG at 80% of its rated power. So let's see this example. So this example for Caterpillar engine, 50 Hz, 1500 RPM, 400 volts. Example here. So the Caterpillar engine, this is the fuel consumption, specific fuel consumption. Let's take one example. The red color is 970 kilowatt engine. So at low power, so this 970 kilowatt, let's say at 0.3 per unit of this power, the fuel consumption is quite high compared to this machine, which is the blue color, which is 1180 kilowatt at 0.3 per unit power. Okay. Okay. So this one not economical when you operate the machine below 0.8 per unit power. Okay, let's take this 0.8 per unit power operation. So the fuel consumption for 970 kilowatt is higher compared to the purple one, which is 1200 kilowatt. So 1200 kilowatt is more economical compared to 970 kilowatt engine at operation 0.8 per unit power. And also at 0.2 per unit power, the fuel consumption of this 970 kilowatt engine much higher compared to the purple one. So the purple one is here. So the size of this engine also should be able to supply load surge power as well. So that's all for today. So we already finished chapter number 4. Okay, thank you.